Power dissipation, as has been mentioned many times previously, the major reason for popularity of CMOS logic is that traditional gates have no traditional gates have no DC power dissipation when their outputs are not changing. However, whenever the output of CMOS, the output of CMOS, output of CMOS, output of CMOS, output of a CMOS gate changes, there is a power dissipation in the gate transistor. The primary reason for this power dissipation is the movement of charge required to charge or discharge external load capacitance and the internal parasitic capacitance. In addition, for input signals with finite and rise and fall times, it is possible that DC paths exist between the power supply and ground temporarily while the output is changing. This is particularly true for large inverters used as buffers. The power dissipated by an inverter charging or discharging a load capacitor is particularly easy to calculate. Consider the inverter of figure that has a square wave input of frequency FCLK and a load capacitance CL. Each time the output changes from 0 to a 1, the load capacitor charged from 0 volts to ED by the N-channel transistor. The energy dissipated in the N-channel transistor during this time is equal to En is equals to CL V square ED by 2. Here you can see the figure. A CMOS inverter with a square wave input at a frequency FCLK. Similarly, the energy dissipated in the channel. Similarly, the energy dissipated in the N-channel transistor when the inverter output changes from A1 to A0 is EP equal to CL E square ED by 2. Since the output changes from A0 to A1 and back to A0 each period T of the input, the total energy dissipated each period is equal to ET is equal to CL V square VDD. ET is equal to CL, ET is equal to CL, ET is equal to CL V square ED. The average power dissipated during a period is total energy dissipated divided by T. Thus, the average power dissipation due to the dynamic charging and discharging of the total of the load capacitance is P dyne average is equal to CL V square ED by T is equal to CL V square ED FCLK. Thus, the average power dissipation is proportional to the clock frequency. At higher clock frequencies, more power is proportionally dissipated. Also power dissipated is very sensitive to the power supply voltage. Increasing power supply voltage from 5 to 3.3 volts decreases the power dissipation by approximately one half. A CMOS gate continuously charging at a minimum at a maximum speed dissipates a similar amount of power as an NMOS gate running at similar speed. This would be seem to contradict the stated superiority of CMOS logic with respect to power dissipation. Luckily, most common chips have tens of thousands of or even millions of gates that do not change in any given clock cycle. For example, in a computer chip, most of the memory and resistors are unchanging in any given clock cycle. These gates do not dissipate power, and the overall dissipation is here you can see the figure, the input voltage waveform and the direct path current of a CMOS inverter when the input voltage has finite rise and fall time. Much less however, for particular case of a CMOS gate changing continuously at full speed, the designer might consider logic gates that have DC power dissipation. If smaller size or greater speed results, the overall difference of the power dissipation of the total chip will be small. For this case, this will be his there is addition power dissipated over and above that given by equation. His additional component is due to the fact that during transition there is some DC current going through both the P channel both the P channel and N channel transistors at the same time. This current is often called the direct path current. The addition power is usually less than 20% of that due to the charging and discharging parasitic capacitance Wenrick 1984, but can be substantial, particularly if the input changes slowly. This power dissipation can be can be estimated among assuming area under a plot of the direct path current of an inverter can be assumed and can be approximated by a rectangular wave. Rebly 1996, for example, consider the plots of the input voltage and direct path current of a CMOS inverter shown in figure. Once the inverter threshold voltage VTH has been found, then the peak direct path current is found. I peak is equals to nu and C naught x by 2 the W by L1 VTH minus VTN whole square, where it is assumed that the N channel drive transistor is Q1 and the energy dissipated each period is then given by EDP equal to VDD I peak TR by 2 plus I peak TF by 2 equal to VDD I peak TR plus TF by 2. The average power dissipated is the energy dissipated per period divided by the time of the period. Thus we have a PDP minus average equal to 1 by T VD IP TR plus TF by 2 equal to VDD IP TR plus TF by 2 FCLK. Thank you.